Femi Paul. He's a researcher from the University of Ilorin, and then is in the Department of Statistics. So, with your favorite emoji, I would like you to welcome Adeyemi as he takes the mic. So, over to you, Adeyemi. Okay, so as you join the meeting, kindly drop your name and where you're joining from.
Hello, sir. Hello? Hello? Hello.
Yes, maybe we can hear you.
All right. I can hear you now. All right. Okay. All right. If you can hear me, let me hear you. Hello. 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 I don't know if you can hear me. Hello.
No, we can.
Okay. All right. So I think we can start now then. Okay. First of all, my name is Adeyemi Uluwafemi Paul. All right. So today I'm going to be taking you on linear regression using R, and we'll be taking a case study of student performance. So in order for us to be able to get the data set, in order for you to get the data set, you get it from machine learning open repository. So I think that's very easy. You can just come online and type, sorry, I'll share my screen now. Okay. All right. So you can just go on online and type student performance. I don't know, I'm trying to share my screen here. Okay. Hello, can you hear me? Okay, so if you get the student performance data set, you can open it. You'll find about 3 folders therein, and on one of it, you see student.csv. It's that student.csv that we need here. You can download all you see, but you need just student.csv. Okay, so if you have your data, I believe we can start, but I'm going to still illustrate it here. I don't know. Okay. All right. All right. Now, if you go to, you can just type it on Google, student performance data set. You have that on Google, you type it, it's going to bring some things out like this, and then you click on student data performance data set. And when it comes out like this, you can now click the data folder, and then it will bring out a number of things like that. Parent directory, student zip. Hello, sir.
Okay, so I'm sorry to cut in. I think we cannot see your screen. It's actually static here. Only what we can see from is Cora classification. I don't know.
Cora,
Probably you
okay.
can stop sharing and share.
Okay. All right. I'll work on that just now. Just give me a few seconds. I should be able to fix that. Okay, so sharing my screen again. All right, I believe you should be able to see this now. Hello? I believe you can see my screen now.
Yes, we can. Yes.
All right. Now, so as I said before, you go on student performance. Okay, just write student performance data set, machine learning repository, just the way I've written mine here. If you can see it, student performance data set, machine learning repository. So you just press, you click enter, or you press enter rather, and then you have a student performance data set. So if you can find this option here, you just click on it. So the student performance data set. So when you click on it, you'll find a data folder. Data set description talks about everything you need to know about the data. But then you need to click on data folder. Okay, and then you click on student zip, not student old zip, student zip. And so when you click on that, it's going to ask you if you want to download it. So you download, and I have it already, so I don't want to download it now. So then you unzip. So you're going to have a number of folders. I'll share screen again. All right. So you have a number of folders there, and then that way you, okay, maybe I should just download it to make it easier. So let's see how it goes. So we can follow. So you click here, and then students, if you have it already, okay, like I have mine now, I can open it. And going back to where we started from. Okay. So I come here now. I have it already in my system. So just click on wherever you have saved it, wherever you've downloaded the file to be. And here it's on R tutorials. Okay. Now, so you come to R tutorials and then you go to students, wherever you might find it. This is the zip file I have unzipped. So, but if you click student zip, it's going to bring about four about 4 different, okay, so yeah, it brings about 4 different files, but we're going to be using only one of them, and that will be studentmaths.csv. All right, so if we copy that, I believe we got that. Now, so you need to look at your interface in R. There are a number of, okay, there are 2 interfaces you can use for your R coding. You can use the ones I know. You can use the normal R, just the R package itself. When you open it, it has a small editor that you can use for editing your code. Apart from where you run your code, it has a small editor. I'll be showing that shortly. Or you can, if you have the other coding, maybe like an IDE that allows you to use R, that's also very good. All right, but I'll be using, basically here, I'm going to be using just the R software itself, and I'll be using its small editor there. All right, so I would like us to follow. And so in order to do that, okay, so you can open, if you have an R editor like the one I have here. On Windows, it's going to be slightly different, or you take a different shape anyway, but still the same R. This is my console now. So you can click on your R and open it. And you'll see that if I write anything, it's not making sense. It will bring some things that are funny. Although this one is bringing a function here. So if you have we're not going to be running our code here. If you have opened your editor, if you are using something like my own, you just need to open an R script. You can click on, depending on the way it writes open, like in my own here, it has regression. Okay, this is what I want to open now. I have something written already. But if you want to create a new file, you need to click wherever it says you should create a new file. So let me expand this, make it bigger. All right, so, okay, I think I have to make it smaller. My screen is a bit small, and I may not be able to see. Okay, I think you can load a new script here. And so something like this now, so it's there's nothing there, and that means you have to, whatever you're writing, you save there. So you can write your code here. It allows you to edit, to add anything you want to add, and subtract anything you want to add, subtract, clean anything you want to clean. But if you write here, it's going to be a bit messy, because at some points you will not be able to correct, or might not be able to flow well with the program. All right, so getting back to our data. Now, how do we load our data? Before we go on, I prepared a slide, and I want us to follow it very well. First, we need to know what we call our regression there, but we need to load our data and everything. But what are we doing? Why are we doing what we are doing? No, there's an adage says, when the use of a thing is not known, abuse is inevitable. So I'd like us to see something first, then we continue there. So I prepared a small PowerPoint. I believe at the end of this class, everyone will be able to get that. Now, it's, okay. All right, so regression analysis using R. All right, so you find that table of content, what we'll be studying, we'll know what regression is, what exactly are the X's and the Y's, the estimate of the BI's, estimating the sum of squares, and some codes that we can always remember. So, and then regression analysis using the LM function. Now, coming back, okay, now in continuation, we see what is regression. Now you need to understand the concept of regression, because when you don't understand it, you just work with the codes, you don't really get anything important. Regression can be defined as a statistical technique for estimating the average relationship between a dependent variable and at least one independent variable. I believe that if we remember those days, we talk about straight line equation. One of the things that was, okay, one of the ways by which it was usually represented, if you remember, was the use of an equation like y equals to mx plus c. That expression was very unique those days, if you remember. And when we say y equals to mx plus c, we say m is the slope, the c there is the intercept, and x is a variable. So and y is also a variable. So x is independent, y is dependent. So if you get a value for x, you can get a value for y. And so regression takes looks at defining the relationship between x and y, so that if you know x, you can find y. All right, so but the x we're talking about can be one, can be two, can be many. So what we are saying is that those dependent variables can be more than one. So if they are more than one, then you have it might be linear, but you have more than one variable, so you can call it a multiple linear equation, a linear regression equation. So now, what we have seen that we are trying to find the relationship between x and y. So if you follow the slide, you'll find some expressions I've written here. The simplest form is when you have just one independent variable. So, and that is x, if you can see. So that is x. And then in my expression, you find an e there. We call it the error term, because in statistics, we believe that nothing is free from error. When you do your things, they are probabilistic, so random, so you can find errors there. So we have to account for that. All right, so if you check what is on my screen now, you find another expression here, but this time around, we tend to have just x1, not just x again, but x1, x2, up to xn. Now that means we have n variables, n independent variables, but we have just one dependent variable as usual. And so this is how we relate them. So you find that it's a linear equation, a linear relationship, so that when you know the values of x1, sorry, this is not supposed to be there, x1, x2, x3, x4, up to xn, then you can find the value of y. All right, so at whichever stage it might be. All right, so then we have this equation in matrix form. You can see that here. Matrices make it easier for us to run whichever code we are running, or rather to write whichever algorithm we're writing on R. If we have to write everything like using the summation sign and squares and the others, sometimes it might be hectic, it might take a long time. All right, so then an estimate of y assumes that there is no error. So when you have when you estimate R, like the expected value should not have any error. Okay, so that's that about that. And so what exactly are the Y's and the X's? As before I go on with the coding aspect, you find out that your Y is dependent, X is independent, as I said before. So suppose we look at the age, weight, nationality, gender, and score of the student. So you find out that you can easily say that his age, rather his score, should depend on the others, or at least some of these other variables here can be just on age, or age and weight and the others. So you find out that in this situation, the score is the dependent variable, that is y, and the x's are any of the other ones, any of age, weight, nationality, and gender. So it is possible that a person's score can depend on the gender, nationality, and the others. Okay, so in order for us to be able to estimate, or rather get that regression equation, we need to be able to estimate some things. And one of those things is the beta. Okay, I call it beta here, although I wrote B here, but usually call it beta in statistics. Actually, these ones are the coefficients. When I was looking at this the other time, we had beta 1, beta naught, beta 1, beta 2, beta n. Okay, so B is the vector that contains all of those B's, so those betas, whatever you call it. So all of those coefficients of the X's. So now, the formula for finding B is the inverse of X transpose X multiplied by X transpose Y. So that's how that one works. All right, so we go on, and then we find some other things we need to estimate. All right, so one of it is the sum of square regression, and this is the formula. So if you have gotten your beta, you can say beta transpose X transpose Y minus the correction factor. The correction factor is the square of the sum of the dependent variable rather divided by n. So it's a very simple thing. We're going to see that illustrated shortly. And then the total sum of squares is a SST. It's giving us Y transpose Y minus correction factor. Don't forget that this, what we have seen here, and even the last term here, the error sum of squares can be expressed as in summation sign, using summation sign. But we're not doing that here in order to make the work easier. All right, so the last one, the error sum of squares, SSE equals to SST minus SSR. So that's going to be Y transpose Y minus B transpose X transpose Y. All right, so you can just get it from here easily, but if you want to use this, it's also possible, and to give you the same thing. All right, so that's that about that. So there are some, I believe we can see this from here. When we get the slide, it will really help us. So there are some codes that we need to be familiar with, but I'm not going to be doing them here on the slide. I have it prepared already, so I just go over them. So if you know these codes, they make things easier for you. All right, so going back to R, now we'll find what we are saying. Let's start. I'll be using my console this time just to illustrate some of those things, but I have it prepared already, so it's easy. The script is ready, and once we're done, I will be able to send the script. All right, so this is it. Let's start. What exactly are we doing in R? R is a calculator. R is a statistical package. And for instance, if I have some, like a variable, let's suppose we name it age. Age is equals to, let's suppose the age of somebody is 10, another person 20, another person 30. All right, so I'll stop there. And we want to find this age. We want to find some things about this age. R allows you to create what we call a vector. And that vector is what I have written here. You've seen it here now. The age equal to this. So you can just write age, or if you like, print age. So whether you write age or print age, it gives you the same thing. All right, and that will give you those values. But then we should be able to find the mean or sum of the age. So let's see, sum. If we want to find the sum of the ages, just put this here, we get that, and we can find the sum to be this. Okay, no, 60. And then the mean of it, we can find it. So the mean of age, so that is 20. All right, so now this is very basic, but then that's not all. There are other things like the range, the standard deviation, so this one will give us standard deviation. I just write ST there. And it's better you save whatever you're doing in a variable, as I've done here, like saving one in sum, saving the other in SD, because it makes your work easier, and you can always take whatever you want to take. Maybe you've done it like 4 or 5 lines before where you might be presently, and then you can just take it. But if you write it like that, just say maybe SD age, it will just be there. You can't use it anymore. So that's it. All right, so then you can find the variance of age. So the variance of, sorry, VAR actually. So the variance of age will be written like this. So you can say variance, and it gives you that. So there are a host of them, but for the purpose of our lesson, we'll be needing just a few of them. All right, so let's see. And if you want to find, let's suppose you have 2 variables. We have age to be equal to, let's say, whatever, okay, that what we have defined before. And then we have height to be equal to, let's suppose, don't mind me, we're just using, don't forget you have to put your C outside, you concatenate. And then we have, let's suppose 30, let's suppose we have 40 like this. don't mind the height there. I'm just writing that randomly. All right, so if you want to find the correlation between these two, we do correlation age and then height. All right, so it will give you the correlation. So you see there's a large, like a positive, highly positive correlation between these two. All right, so as the age increases, the height increases. All right, so that's how that's that about that one. All right, but in looking at this, we might also be interested in finding the covariance. So the covariance will be written as covariance, that will be curve, so age and height. Sorry. All right, so the covariance is 150. Okay, so that's that about that. All right, so in continuation, there might also be need to check a lot of other things, but I think these ones are sufficient for now. All right, so the next thing is let's look at what we call matrices. How do we make a matrix? A matrix, if you know in linear algebra, mathematics, say a matrix is an arrangement of numbers in rows and columns, or you say a collection of vectors, like that. So now when we have, let's suppose we want to have, we have a matrix A. You know, in mathematics, we use A capital to represent matrices, but in programming, it's advisable to stick to your small letter. All right, so you have matrix. This is how you make a matrix. Now, let's suppose we're making a matrix A, right? Matrix A equal to, now you will need a vector in here. And this time around, I want to use these two vectors. You can define by using concatenate, put all the values you want to put, and then you arrange as I'll show now. But I would like to use, okay, let's just do it in such a way that we're going to have, okay, there's 6 numbers here. You have, this is what you want to make a matrix. Now it's a vector. This is what you want to make the matrix, but it's a vector. But you can specify the number of rows you want. So n row, that will give you the number of rows, and you write, let's suppose we want 2 rows and 1 column, and 3 column actually. So we are going to have n col equals to 3. Now, what you have as the number of rows and columns, when they are multiplied, that is 2 times 3 here, it must be equal to the numbers you have in this vector. So there are 6 numbers in this vectors, and when you multiply 2 and 3, that gives you 6. All right, so that's that about that. And then you need to specify another thing called by row. By row, is it true? Is it false? There are 2 ways to specify true in R. You can say true, like capital letter TRUE, or you just say T. Whichever one you use will work, and that's how to say it. So this will give us a matrix. Now you find out that because I said by row is true, it arranged the numbers by row. So after saying 1, 2, 3, it came here and did this, and it came to the second line and did 4, 5, 6. So if it were to be by row is false, we can check that. You will see that it will arrange the numbers in terms of column. All right, so in terms of the column, you find out that the first number and second number went in the first column, 3, 4, next column, 5, 6, next column. So that's how that is done. All right, so that being said, we need to go into, okay, so that's that about matrices. So, okay, let's do basic operations with matrices. You can add matrices normally. If you have a matrix A like this, just, you know, the matrix being conformable, the rule there. So you can do another matrix. Let's assume the matrix is this. We have B, and here we have 2, we have 3. Okay, let's just assume, all right, 1, and then 0, and then 0. Okay, so we're good. All right, suppose this is the matrix you have now. We can say another matrix C is equal to matrix A plus B. So that will give us C, and this is, so you can add. You can say another matrix D will give us A minus B, you can add them. So check B, this is what B gives us. All right, so you can also divide and do all of that, but I want to go to transpose of a matrix. So the transpose of a, right, that as trans A, or if you like, let's make it shorter, AT, so A transpose, that will be TA, like this. And so that will give us the transpose of A. So if you want to check, you see this is what our A was, you can see that the A has been transposed to this. All right, the A has been transposed to this rather. All right, so that's that about A transpose. And then when you want to find the inverse of a matrix, you can't find the inverse of a matrix like A here because it is not a square matrix. So I'll have to make a square matrix. Let's see what I can do. All right, so just like before, we'll put 3 here. Let's see. Okay, something like this. Just try to be careful to make sure that your matrix is not square and singular rather. That means you will not be able to find the inverse. So I'm looking for the inverse of this matrix now. Sorry, let me write this here. Inverse of a matrix. So the inverse of the matrix can be found. Okay, this is B. So can be found by saying, let's call this B inverse, solve B. All right. So when you say solve B, that gives us the inverse of B. All right. So this is the inverse of B. And if you multiply the inverse of B with B using the matrix operation, matrix multiplication, you are going to get the identity matrix 1, 0, 0, 1, that kind of thing. So we're going to do that. But before we do that, we need to do what we call matrix multiplication. Okay, so matrix multiplication. Now the matrix multiplication is different from the normal multiplication. I know, like I said, R is a calculator. For instance, if you say 3 times 6, you know, let's just, okay, we can just do this like that. You get 18 like that. But when you want to do matrix multiplication, you don't do it that way. Okay, so this is what we do. Let's assume we already have, all right. Okay, let me define another matrix, matrix C. Don't forget we have matrix B to be this. All right, I want to define matrix C now to be equal to matrix. Let's have this 1, 2, 4, let's assume 3. All right, so number of rows 2, number of columns equals to 2. If you omit the by row by column thing, it will take it by row. You can notice, or rather by column. Okay, so you can see that it takes it by column if you do not write by row equals to true. So that's the default. All right, so now we want to multiply these two things. How do we multiply them? Let's call another matrix E, matrix E. So when you do matrix multiplication, you say the first matrix you want to multiply, then you put the percent sign, and then the multiplication sign, then the percent sign again before the next matrix, the matrix you're multiplying with that matrix. So let's assume the first matrix was A, could be C, could be anything, as long as it's conformable. All right, as long as it's conformable to matrix multiplication. All right, so you, as we said before, you put the first matrix, then a percent sign, then a multiplication sign, then a percent sign again. After the percent sign, then you can now write the next matrix. So all right, it says you're not conformable. Let's see. I think, okay. All right, sorry. B was the 2 by 2 matrix I defined earlier. So we're going to put B here, and C I just defined. Okay, now so we can have a multiplication. So this is the result. All right. Now, in order for us to be able to check, we found the inverse of B earlier. So let's see if we're going to get the identity matrix, as I said, if you multiply B by its inverse, So if we put that here, we're going to have this, all right? So if you put E, you see we get 1, 0, 0, 1. So that's the identity matrix anyway. But sometimes, depending on the kind of numbers you have, you might have something like 0.99999, like 0.9 raised to the power of something here, and then that's here. And then here you might have 0.0000 maybe, or 0.1 times 10 raised to the power of, whatever, maybe something like that. And, that might not really look like the identity matrix. So what you just need to do is to use a function we call round. So in that case, you're just going to say E equals to round and then you have E, then the number, you don't really want any number of that, so you could just write maybe 0 here, and then put it to not, so it will take care of all the decimals. Round means round E, round this E here to this number of decimal places. So it could be 0, it could be 1, it could be anything, it could be 4. Usually in math, we use 4. But if you want an identity matrix and doesn't look like it, you can use that. All right, so that's that about that. The last thing we need to check is the data frame. The data frame. We'll write it like this. Okay. Now, the data frame is very simple, and it comes from, okay. Sorry, before we go on with the data frame, there's something I didn't touch in the matrix. The other time I was trying to write a matrix. So if you have a matrix like this, and you have 2 vectors already defined, you don't need to go and start writing something different. You could just put, supposing I have A and B, and I do, the vectors are defined earlier. You can see A here, and this is A, and there is also a B. So if you have these 2, writing them like this will bring a matrix. So matrix C, you can see that already, like you put those 2 together and then it gives you a matrix. So that's that about that. So it depends, but I think, okay, when you work out that on your own, you can try it and see what kind of results you get. All right, so data frame. The data frame is more or less like a table. When you talk about your table in maybe SPSS and the others, you have a table where you can input your data. The data frame is something like that. But R being a command line, you can still view and even edit your data the way you do on SPSS on R, but you need to use something which I will show shortly. Now, so how do we define the data frame? Supposing we have a vector, I'll define new set of vectors. Now, let's suppose we have a vector X to be equal to this here, and we have another vector Y to be equals to this here. Let's say 2, 3, and okay, let's have it to be 5, 3, and 4. Now you can have a data frame, just define it as, you can call it whatever you want. And then you say data dot frame. Then you put X and then you put Y. All right, so that will create a data frame for you. You can call its name, and this is how it displays. And then if you want to see it in a way where you can maybe edit it or see it in a tabular form, you need to write view X, Y. Okay, so there is something my system is telling me here that it's missing in my system because I'm using a Mac. On Windows, I don't think you're likely to face this. So I can use this until I install whatever is saying I should install here. So you can work on that, but it's not so necessary for this tutorial. All right, now, so the data frame, you can see the individual vectors, or you can obtain the individual vectors of this data frame. And how do you do that? For instance, you can say X equals to data, and you just put the $sign, and then you write X. That will give us the X column. Okay, sorry about that. I wrote data, actually it was data frame. Okay, so that's that. So it will give us you can see now it gives us the column for X. That's 1, 2, 3. But if you want Y, that of Y, it's the same thing. To give you, just put your Y, and then you get, that's that about that. Okay, so that's that. We're going to be using this in this tutorial. So that's that about, basically that's what you need to know, okay, about data frame. There are other ways of working with data frame. There are other things you can do. For instance, you might like to know the column names of the data frame. So if you want to know the column names, you can write column names. Okay, let's write it as column names equals to column names. So you write that, and then you put your data frame in the function. So when you press column names, it will bring that out, and so you have X and Y as the column names. If you want to rename the data frame, whichever one you want to rename, you just write column names, and then you put the data frame again. if you are renaming the first variable, you put whatever you want to name it. Let's suppose I want to call this R now. So when I press, I type data frame and I call my data frame. Now you see that X has been changed from X here, it has been changed to R. All right, so that's that. That's how that works. All right, so now I think we are ready to start the regression analysis. We can make our model now. Assuming okay, so how do we load our data before we start? Your data will be located wherever you have saved it. For me, my data was saved. So if you let me share some so you can see how, supposing your data was saved somewhere here, like in my case, this is where my data was saved. In this folder right here. So you can go there and just, if you're using a Mac, go there and write, I think there's a place where you say get info. Okay. So get info, then you can copy this. Okay. So when you have, oh, you might not be able to see. I don't know if we can really see what I'm doing. Okay. So you can, okay, get info. So when you get to the get info here, you can click. Okay, you can just copy this. So it's copied as path name. If you're using the window too, it's similar, but you might have to click the top, I think where the file. You go back to R. I'll start doing that now. You write your code on your editor. I will be doing that very soon, so that when I'm done typing, I'm correcting, I can just bring them here. This one was just to illustrate. You find out that this error, some of the errors that we're showing, if there are so many, you can no longer, you might be confused depending on, well, so you'll definitely be confused seeing this red thing here. So it's better you just don't use it. But when you're done, you just copy your codes and paste. All right, so now, going back to the editor, I want to go back to my editor now. Okay. This time I'm using this now. I can write, okay. Whatever you copied, don't paste yet. You can just hold it. All right, so just write data. The data we're loading is equal to, you need to use something called read.csv. So read.csv, then you can paste this. But what you have here will not work well for you. You'll need to change it. It's not going to work. You need to change it to a backslash. So you have a forward slash, you change it to a backslash. So I think it's the same thing on Windows. Change it to a backslash. Okay, so then my folder was student, but the file itself is student math.csv. Okay, so you need to work with that, just change that and make sure it's okay. And when you're done, you put this in quotes. When you're done, but you're not going to stop there. You have to go and write another thing called SEP. The SEP here, when you check your data, the data we have, you can try checking it on maybe like maybe Microsoft Office or something that you have, and find out whatever the data is made up of, like to see its constituent. So if you check it, you are going to see that there is a separator that separates whichever value you have. Sorry, I'm putting this on, trying to see if I can. Okay, see if I can open the data. No, that's not. Open. So I want to show us so we can see what really happened in the data there. I don't know why this is not okay. Okay, for whatever reason, it's not opening, but you'll find out that commas are separating that one there. And so I just go back. So save time. So when you open the data, maybe we can check it. I've just, okay, all right. So I think we can see it now. So you're going to see those commas there. That's why we're putting sep comma. I mean column, not comma in this case. Sometimes it can be a comma. So if you can see this, you'll see that each value is separated by a semicolon, semicolon, semicolon. So that's why we are doing what we are doing. I don't know if you just open it. If you have the data, open it and see, you see what I'm talking about, even if you can't see my screen. All right, so that's that about that. All right, so we come back to our editor. Now you have that separator there for that reason. So even if you couldn't see my screen, I believe if you checked it, you'll find that. All right, now, so the next thing that you do is now try to see if your data is loaded correctly. Let's see, we want to see that here now. I didn't copy the stuff well, so I'll go back. If your screen is too bulky, you want to clear your screen, you can use Control L on Windows, then Control Option, okay, Option Command L on Mac. So we have our data. So just now you see that this is a data frame. It's bulky, it's not looking. So you find out if you can see it well, just check 395 rows long. So to check the number of rows of your data, there's a way you do that. But let's check the data head. So you could just say head data. I called it data. So the head data gives you an overview of a number of some lines. I think the first to the sixth line number 1 to line number 6, so row number 1 to row number 6 of the data. And so this is how it looks. All right, so you can also check the number of rows of the data. So if you want to check the number of rows and row data, that's going to be 395. And then number of columns of the data, that's going to be 33 columns. So if you want, you could just say dime data. So that's 395 by 33 by 33. All right, so that done, we can now go back to what we were doing. Okay, so we have our data there, and I don't know, you might not have seen what I did on my, okay. So let me share screen so I'll show what I did again. Okay. All right, so this is what I did. I think we couldn't get that. So, okay, let's do it again. So we have the data I loaded, copied and pasted like this. So let's see. Sorry, just saying something about hexadecimal, this, that, and so just check it and see whatever might be the issue. Okay, I think you use a forward slash, not a backslash. All right, so that's clear. So this is how you write it. So when you have written it, you can check the head of the data, just say data head. It gives you a few, just some row number 1 to row number 6 of the data. All right, so that's that about that. And then you can check the number of rows you have. So this is just row number 1 to row number 6, but you want to check the number of rows we have. So n row data is 395. Then n call data number of columns is 33. So you could just say the dimension of whatever it is, sorry, of data. So you have it 395 by 33. So that's that about that. Okay, I think we're good with that. All right, so the next thing we need to do is so now begin to use our data. So I'll go back to, so don't forget to change this. Yeah, so it reflects here. I've changed mine there, but this is where we want to use it. So now that we have this, what do we do with this? First of all, we want to write, it's possible you can go into like checking the correlation between this variable and that variable, but I'll not be going there on account of time and on account of the objective in this place. You just want to be able to run the regression analysis. So the first thing is that I would like to convert this to a matrix. There are two ways. I'll go with the first one, which is a matrix, so we can get used to the matrix method. So let me call this X. First of all, before I do X, I want to write another, I don't know if you can see this clearly, so let me make it a bit bigger. All right, I want to write another, or rather a vector, and writing that here, I want it to be a vector of ones. I'm calling it I, to be 1, and it will be repeated the number, repeated a number of times. Rep1, sorry. So the rep something, just repeat A, B times. Okay, so that's what he says. So I'm repeating 1 this time, and the number of rows we have in data, and that's going to be 395, as I said before. All right, so that's what I want to do here. And then I want to make a matrix, the matrix I talked about, the matrix X, that's the X matrix. The X matrix consists of the variables we're interested in. Before making the X matrix, I need to find out what are my dependent and independent variables. So in this regard, in this case, my dependent variables, there are many variables here. Our data set talks about the scores of some students. So let me go back to this so we can see what I'm saying. Okay. Now, so you can find a number of things here. You see school, sex, age, address, family size, parent status, and the others. And then you have grade, the first grade, second grade, third grade. And these grades are actually the grades of students in mathematics. All right, so now a student having an age, a particular age, and then it scored something in the first grade was this, second grade was this in mathematics, and this is the third grade. I want to create a scenario here. We can assume safely that the age of the student affects his grade. All right. So, and that the grade of a student in the first math test, that's G1, and his grade in the second math test, that's G2, will affect his grade in the third one, G3. So he can be unserious in these two, and then when he sees that the results are not good, so maybe he becomes serious here. Or he can, maybe because he did well here, he will relent when it comes to this one. So let's assume that. So that means we are going to have G3 to be our dependent variable, that's the Y, whereas we're going to have G1, G2, and the gender to be our independent variable. Now, so that will come in handy. Before, we cannot write our X yet. So going back to where we were before. All right, so in our editor, we have to write all of those other ones. So I just bring out the age, G1, and the other. So let's have age to be data. So we have age, and then we have a G1, but I'll call the G1 here, please. So small letter, preferable. G1, and that will be capital letter G1. Then G2, that will be data. So G2. And then finally, we have a independent variable G3. So I'm going to call that Y. Let's just call that Y. That will be data. And then we have G3. All right, G3. All right, so that's that about that. If you want to run our data now, we can copy and paste there, but I will not copy and paste yet. I want to just work on it. Okay, until we get to a point where it's okay. So let's see. Now, how do we make our X out of this? We can decide to put our X here. So this is the dependent variable. All right. Now, how do we put our X here? Our X here is going to be a matrix, as I said before. So we can just put that matrix here, and then we'll have the way I did the last one. So the second way you can use your matrices, you put age, you put G1, and then you put G2. Now, so we have a matrix, but I have to specify the number of rows, and the number of rows should be the number of rows in our original data. So that's that. And then number of column should be 1, 2, 3, 4. So that should be 4. That's 1, 2, 3, and 4. Okay, so that's that about that. And we need to specify one more thing. We can leave it, but if you leave it, it's going to still take it the way it should be taken. But by row first, the same thing. It's default. It's there by default. So I think at this point now we can check what we have done, and we go back to R. Sorry. All right. So in here, you can paste your code, and then so if you paste the code, we can now check our X. I would not like to display everything, so I just use head X. So okay, no, we can't use head X, yes, because this is a matrix. So I just write the matrix here. So you can see that I have a matrix that is such that we have the first column to be a column of X's, or sorry, a column of 1, and then the other columns are those of age, G1 and G2. All right. Now, so we can go back to our editor, and okay. Now, we can now look at some of those equations I've talked about before. I'm going to show it again. They're in the slide. So I talked about them earlier. Okay. Sorry, I might not be able to open the slide currently, but I think I've closed it. All right. So I talked about them in the slide. Let's see. Let me open it. Okay. Sorry about this. Okay. I think I can just write them myself again. So just come here and write them. All right. So I talked about a situation where you want to find your beta, and one of it was beta equals to, okay, you have X transpose. Maybe I think X transpose, the inverse of X transpose X. So multiplied by X transpose Y. So if you want to put this here. All right. Now we're going to use that. I've written that before, and we will need that. we're going to need that. Please just give me a short time. I want to put a slide on so that just find the stuff to use it. So all right, so now sorry. All right. Now in continuation, we can look at the slide now. Now, sorry, this not. Let me remove this. Anyway, let me just show us something from here. So we have this here. This is now. That's what we want to write. But it is written like this. All right, like this. And if we copy this, except to change this back to small letters, they are not likely to work as much as they should. Now, so what you see here is a very simple thing. If you don't mind the fact that you're seeing all of this percentage and the others, actually, so they're very simple to write. You just need to master the rule. All right, so we'll go back to our editor and we can now work on that. Now, so we're going to write that. Now, so it's going to be solved. First of all, what we are saying is that, okay, let me put that here so that we can see it. I'll clean it very soon. So I'm using the small letter, as I said before again. And the inverse of X transpose X, remove this, of X transpose X, just this, is said to be solved. Now, X is, don't forget, X is small letter. So we just have to transpose. This is X transpose, S transpose X. So transpose X. And then we're going to put this percentage sign, and then we're going to write this, and then we're going to write this. Get that now, and then we are going to write this. We put X here. So this takes care of the second X. So that means we have taken care of the inverse X transpose X. That's that about that. So that's very simple, you can see. Then, but because this on its own is a matrix, we are going to have to put a percentage sign here. Then we'll put this, then this, and then we have an X. Okay, sorry, small letter. X again, but this time transposed. Let me separate this from this so to make it easier. All right, so I believe we can see this now. So we have X here. I'm working on that now. Okay, so that's transpose X, this one. Okay, now after working on that one, we put the modulus, or rather the percentage sign, then we put the multiplication sign, then the percentage sign again, and then I put my Y, you put the Y here. All right, so that takes care of the second part. Now you find out that it's easy. So the percentage that is coming outside and the bracket outside, this bracket, the percentage here, is to show that the whole of this expression is also a matrix. So you just put everything together, and then you come here, and then push this back here. All right, so that takes care of that. So we are done with this one. So we don't need it, but if you like to keep it as a reference, you can just comment it, and that's not an issue. All right, so that's that about that. Now this takes care of, so I'll call this the coefficients. Okay, now we can easily find it. So you just need to, you don't need to copy all your code again because the ones we ran before, they worked. So but if you like, you can copy everything depending on you. So if you like, you can copy everything, but once a line has worked, you don't need to copy it again. All right, so we'll go back to our editor. And then if you like, currently you can clear screen. So I'm using option Command L, you can use Control L on Windows. So just put B. All right, so when you put that now, you see we have an estimate for the B's. So the first one, B naught, beta naught, or beta, B naught, whichever one you call it, that's the intercept, is this. And the second one, that's B1 is this, B2 is this, B3 is this. So this, the coefficient of X1 is this, coefficient of X2 is this, and then the coefficient of X3 is this. All right, so that's that about that. And we can now go on and write more codes to arrive where we are going. Now, what are we left with? We already have our estimate. One of the things we can do is to write this in the data frame. I think we can go back to our editor and just write it there. But if you, okay, let's just write it here in case so that whoever needs it can always go back and get it. So you can say result equal to, so make a data frame. Sorry. Okay. Result equals data frame. We make a data frame, and that data frame, we are going to name it result. Okay, we've called it result already. Just that data frame, we are going to put some things there. So let's say intercept. We're going to have B. This is indexing in a matrix indexing. So since this is a column matrix, similar to a rather it's just a matrix with one column, you can call it a vector. We have B naught, so that's the first one. The first thing we have in the B, that was 0.57, if you check it, something like that, and it will be the intercept. The second one will be that of age. If you haven't forgotten, B0, sorry, 1. Then the next one will be that of G1. That's G1 equal to B. Sorry, this is not the same as Python programming. It starts from 1. The indexing starts from 1. Python programming, JavaScript, and the others use their indexing starts from, like, the indexing of those languages starts from 0, but the index of R starts from 1. All right, so you have this, and then you can now go back and paste this and see what it gives you. So you go back there. Okay, so the problem, what could be the problem? So it says G1. Okay, G1 is repeating twice, so just put G2 there. What could unexpected? So G2, let's see what is wrong with G2. Okay, we don't have a B there, so that's why. All right, so just write result, and then you see we have a neat kind of expression here. So know the value of our interval, know which ones are intercept, which ones are age, which one the coefficient for age, coefficient for G1 and G2, grade 1 and grade 2. All right, so that done, we can correct that here. So this is G2. We can go back and correct it, and your work if you're doing a similar thing to mine like this. All right, so this is G2, and this is, so I have data frame B1, B2. So we might not really need that for now, but we just use it for a comparison later. All right, so that's that about that. Now, but how do we get this, the sum of squares? That's the next thing, sum of squares. The sum of squares, very easy. Also, it's very simple. So what you just do is just write, okay, SSR, that will be the sum of square regression. You are going to have to write transpose B. We are using B transpose X transpose Y minus Y. I believe when you get the slide, you can see that, okay, divided by G, this is going to be square of the sum of Y. All right, so that is, this one here is what we call the correction factor. All right, so that is what we're going to be writing. So starting with this part, we are going to write, this is the transpose of B already, then we need to write the X there. So the transpose of X also as well. Don't forget the sign, then this to show that we are multiplying, doing a matrix multiplication. Then we have X transpose. So we're going to write transpose X. Then we have multiplied by Y. All right, so, but don't forget, we can't just write it that way. We have to put the percentage sign and then the Y. All right, so we've taken care of the first part. We need to take care of the last part. The last part is also very simple. There are two ways, a number of ways of doing it, but to make things easier here, I'm going to shy out of, should I say shy? Okay, I'm just going to leave the matrix multiplication and take a sum. So we just do sum Y square, okay, and then divided by length Y. Okay, so this will take care of it. You can also use n row that n row data here to work out for you too. So, but this will take care of what we want. And then we can have SS total, that's the sum of square total SST. We have it to be, it is written as, forget to comment this out, SSR equal to, all right, so SST equal to Y transpose Y minus what we have here again, the same thing. You just bring that, sorry about that, you bring that here, and that will give us this. Okay, so now we can write that here by just saying transpose. I believe by now you can guess what that is going to be. Okay, so that is that about that. And you can just copy this one from here. It's going to give us the same thing. All right, so that's the sum of square of total sum of squares. All right, so the next thing is sum of squares of error. There are two ways. Either you write it this way, just say sum of square total minus. So if you do a small mathematics here, you're going to have this one minus this one. So if you work out the expression, that's what you're going to have. So I'm just going to put this here. So maybe we'll just call this SSE2. So just to differentiate them. All right, so we can take what we have here now and paste and see what we get. So you go back to your editor. If you're using an any editor that allows you to use the tool to write and run on itself, it's fine. So you go back. Okay, I've returned. Yeah, and then I put here. So you can check your SSR. This is what I'm going to get as you get as the SSR, then SS total, that's sum of square total, and then SSE. So you'll find out that, sorry, there is a small problem somewhere. So let's check it and find out what really happened. So because these two are supposed to be giving us the same thing, but they're not giving us the same thing. So we can check and find out what happened. All right, so you'll find out that I wrote something wrong here. This, if you do your manipulation, actually this is supposed to be the result, not what I wrote before. All right, so if I copy this and go back there and write it, I'm going to have this as the answer. Okay, so you find out that the answers now tally. All right, so that's that about that. That is how to run or to write a small algorithm that shows the regression coefficient work. But this is good if you are trying to make your like get familiar with R. But as a professional data analyst who wants to work on things and get things done on time and as it should, you might not want to start writing all of these because there are already built-in functions for you for various tasks. Many times you have to learn how to use existing packages, so you will not be reinventing the wheel. but sometimes you might have to write your own functions and programs from scratch. So you need to be aware of that. All right, so this is, we can say, my own regression algorithm. Okay, but there is another function called the LM function. Okay, so the LM function is a good function. It means linear model. And what is it good for? It is good for getting everything that you need to conclude on your model. So let's start from, so what we have written here is fine, but the LM function is going to undo this for us in a very short time. So we'll look at that. So just say, we need two things in order to work with the LM function. The first thing is a data frame. We already have that. And then the data frame, so we already have that data here. So data frame, when this is loaded, it loads it as a data frame. Okay, so we can have model. I'll write model here. Let it be model, then LM. So when you write this LM, it takes a few parameters, one of which is your dependent variable written like this. And then if you want to regress this with all the functions, or rather all the variables in the data frame here, in this data frame, then you can just put a dot, and then you can write data equals to data. The data here is a parameter that takes in some argument here, or what is the other way around? You can say argument that takes in some, well, we get that now. So this one is built in. This data here is not built in. This one is coming from here. Okay, so this one is this one here. Why this one is an attribute of this function. So it's one of these things there. So it's a parameter. It can't be changed. So you have to write data here, but this can be named anything. All right, so when you have done that, you have dot here. You can remove this if you don't want to regress y against all the independent, or rather all the variables in this data here. All right, so I picked a number of variables. I just need to know their names. I need to know their names. So you can go back to our data when we said something about our data in there, and that was when we said data, okay, call names data. All right, so this will show the, even if we didn't do this before, I believe we have, okay, we did it before we started looking at this data we're looking at. All right, so there are a number of things, names we need here. One of it is age. We need this age. Another one is G1. We need G1, and then we need G1, G2, and G3. So I believe we can remember their names. You need to use the names that are defined here for what we are going to be doing. If you use a name that is not defined here, you are going to the computer R is going to tell you that the name not found, variable not found. Okay, so that's that about that. All right, so we return back to what we're doing, and then so we have to put those names. Which ones are we regressing? You can see them here, age, but we used capital G1. If you find what we saw when we checked the column names was capital G1 and capital G2. So we cannot use small letter G1 and small letter G2, just like we had to use them here. All right, so in that case, our model is going to be written like this. All right, so now that we have written the model, with just one blow, we can get what we are looking for. So we just need to take this, just write summary. No, don't write model, write summary. Can get a summary of our model, summary. That will give us, okay, first we need to print the parameters. So you want the parameters, just write print model, or just write model there. I want us to see that. So summary of model will give us some coefficients, and okay, the estimated coefficients and their significance. All right, so we can look at that. You just have summary Okay, we have summary there, so we can say print summary. All right, so, and then finally, we want to see the sum of squares. The sum of squares will be equal to ANOVA model. So you can also write that print ANOVA. All right, so we can copy this now and then check these on the work there. So all right, okay. Okay, now so paste that. Oh, sorry, I wrote print ANOVA, but I did not write the correct. It was supposed to be print sum of squares. So permit me, I know the work might look a bit rough, so we'll just go back gradually and see what we have done. Okay, I think we can start from here now. You look at this, you have linear model function to be this, and then when we print it, we get, oh, sorry, there's an issue. We have to go back and fix that. What we have here does not take this. We're not supposed to have commas here, but plus. Okay, so we need to fix that immediately. Go back. So we are going to have so this is supposed to be plus and then plus. Okay, so that's that about that. We can now copy this and take it back. Go back there. Okay, so now that we are back, we'll paste, and then we can now trace. Okay, so we started from here. Now you'll find out that I would like to take them one after the other. We already have them written there, but let's start with some model. Now, when we have model, don't forget there was something we wrote as result the other time. Now you'll see that they look alike. Result was the one we obtained by ourselves, and this model is the one that we have obtained by using the LM function. Now, you might say they don't look alike that much, but if you just use round results and then you put 4, that's the 4 decimal places, round result to 4 decimal, or rather 4 significant figure. Okay, so, or 4 decimal places rather. Here you have 0.5797. So you can see now that they look very much alike. All right, so then the next thing we looked at from the LM function was the summary. So we print summary, and what we get is we still get back those estimated parameters, but this time with a standard error, which we did not do the other time. That will take much time anyway. Then the t-value and the p-values. All right, so from here, we can see that the intercept at 0.05 is not significant. So practically, you say any p-value you obtain for an estimated coefficient that is less than 0.05 is not significant. So it is also not significant here because I mean that is greater than 0.05 is not significant. So if you obtain a parameter, an estimate of a parameter, and the value, the p-value of that estimate is greater than 0.05, right? Yeah, greater than 0.05, then it means it's the estimate is not significant. So it means the age also is not significant, but the first grade, the estimate of the parameter for the first grade now, that's the estimate of the B there, whatever you call it, is 0.0365, and that is significant. And that of the second grade is also significant. So it means that it will make more sense to use only these two when working on the grades. So there are many statistical things that can be done here. For instance, you have the pairwise correlation, the backward, pairwise regression, the backward regression kind of thing, and then you have this stepwise backward forward, so that you can remove some of those parameters that might not be needed, like some of the variables that might not be needed. So that's how to do that. So I think practically we know that two of them are useful to us here. So the next thing is the F statistic that we see here. The F statistic, I'll talk about it before going to the sum of squares, shows something. This model is significant if it is less than, that's the whole thing, not just independent variables here, like not just the parameters that were estimated for the independent variables and the intercept, but everything together, not just the individuals, not just like intercept alone. No, intercept alone is taken care of by the T value here. So the P value that you obtain here takes care of this, whether it's significant or not. All right. That of this one here takes care of the age alone. This one here takes care of grade 1 alone, and so is it with grade 2. But the F statistics takes care of everything. So it's possible that this might be significant, this might be significant. Okay, just like we have it now, this is not significant, this is not significant, but this is significant, and this is significant. But the model in general might not be significant, regardless of whether any of these parameters that were estimated were significant. All right, so if in this case, since the p-value is less than 0.05, we can see this, it means that the model is significant. So the model can be used. But if this were to be greater than 0.05, then the model would not have been significant. So that is that about that. All right, so we'll now go back to ANOVA. So I want to check ANOVA. The result we got, okay, so sorry, the model, we just need to do ANOVA model. All right, so we now have the sum of squares. In this case, you'll find out that the sum of squares is different from what we had when we did what we did. In a way, if you remember, the reason is not far-fetched. The reason is because when we did our own regression, we did it in such a way that everything was added. Okay, so I'm trying to see if I can get it back, but we can definitely get it back. All right, so all right, so right, so we have SSR to be this, and then we had SST to be this. All right, now, but what you have here, you see it now, we have that of age, that of G1, that of G2. Actually, what we have here is actually the sum of these, and this. Okay, so let's try it and see sum 215.9, that is that of age, the sum of squares for age, 5197.2, and then plus, okay, you don't need to write plus since we're using the sum function there. Just need to make this a, okay. It depends on you. You can make this vector. If you want to use a plus sign, you don't need to do this. Just write the plus sign. It will do it. R is a calculator. You need to remember that all the time. All right, so I think, okay. Is there any number I have? Yeah, if you check it very well, you see that I've missed, and I've added a number that is not necessary. Okay, now you see that what we have here now looks like what we calculated by ourselves. Now, having added these 3, 1, 2, 3. All right, so that's that about that. And then the sum of squares total, if you were to add that with the residual, I think what we just did now was to get this and I'm adding the residual now. You have this 58.2. And oh, sorry about that. Okay. 1458.2. Okay, so you see that gives us the total we had. Okay, so that's that about that. And that is how to run the regression analysis, the linear regression analysis. And we've been able to use that. So if you want to interpret your results, what you can say from here is that, okay, not from this place. Now from here is that the grade of the student is dependent on the first grade and the second grade, so that when there is an increase, for every increase in his first grade and every increase by this measure in his first grade, there will be an increase in the score of his third grade. That's the third grade, grade 3, which is our dependent variable. But you'll find out that it is also the same, similar for this, except that grade 2 much more affects his third grade. Look at this now. You can see this 0.97125, which is much greater than this one. So that means his result is much more dependent. His result, this third grade, or in mathematics, is much more dependent on whatever he gets in the second grade, like whatever he gets as the second grade. So if he scores very high, like he scores a very high mark in the second grade, he's likely to score a very high mark in the third grade. So that is what this is saying. And so that is what we are covering, or what we have covered so far. So we can just go back and check a number of things, and then we can call it a day. Now, the first thing, sorry, my mouse is a bit slippery. Okay. The first thing, the first set of things we covered. I would not like to use this space. Let's go back to, okay. That are important is that you load your data. You load your data by doing this. You use the read.csv, and then you get your columns from your data frame by doing this. Okay, so, and also you can repeat a number, this number of times, and then you can make a matrix this way. There is something else called data.matrix. You can try it out. It would have converted our data frame once and for all for us, but you will need to do some kind of a reduction of the matrix, just remove the parts we need. So you can do that easily, sort of using this. All right, so then we went to look for a coefficient. We wrote this to get a coefficient, then we wrote this to get a sum of squares, and that's it. So instead of doing this, we could actually just use the LM function, which is easier, in which case we have to write the model, and the formula has to be correct. I said, if you're using a data frame that contains more variable and you want to use all of them, you can just put a dot here. It will take care of all the variables, but we're using only three, so we have to specify them. And then you can write the summary of the model, and then the sum of squares, and you can now say print ANOVA. So you can get everything you want that way. So I think that's that about that. So that is basically what you do with your regression analysis. There's more to it. There are many other things that can be done. There is something called the read regression. There is the polynomial regression, the lasso kind of, and many other things. But basically, for linear regression, this is what you need to know for a start. All right, so with this, we come to the end of this tutorial. Thank you very much. Hello?
Wow.
I don't know if there might be any question.
Thank you very, very much. Thank you, Kenny, for this. Can you hear me?
Yes, I can hear you, sir.
Wow, thank you very much. Please let us appreciate our participatory favorite emoji. Please let us do that. This has been a fun session for me. I've been following along. I'm following enough for how already. We have low, what's now, we don't have much people that use this, that use high, especially in this part of the country. I'm very excited to be part of this. Okay, thank you very much. I did great with that. See, let us get as well as easy how to celebrate our first week. This has been an awesome and interesting section for myself. I really learned a lot. In Python, we start our counting, our index for what?
From zero.
Yeah,
Yes.
but in how?
You start from one.
So we start from one. So go and get that in the students. Okay. So we have two questions here. Okay, so the number one question is, can you show us how to plot the linear regression curve for the result? Okay, probably because of our time, we will not be able to show us. Okay, but in subsequent sections, we are going to treat that. Okay, so another question, I think it's for me. Okay, so and the question is, there are some, what do we call it now? There are other there are other I know that there are other measures that one can that we use for regression analysis. Okay, so I don't know. Do you also have functions for those models that you can use or you can have? Okay, another thing that very baffles me after just which way is how so we have adopted okay. So can you please answer this question?
Okay. Of your questions, I couldn't get everything well, but I got a few. The first question was that how can we plot a linear regression curve? I think I got that one. You can plot it by using the plot function. So if you go back to your R console and you write something like plots, don't forget our model is this, and you write plot model. Okay, I don't know. I think it should work, but because I've not used this, let me see if I can plot something, see something else in my own code here. Plot, let's see, 1, 2, and you have 3. And then you have 1, 2, 3. Okay, you can plot that. So when you want to do your regression analysis, what you need to do is to first plot the two variables that you are using, if there are two. I don't know if you get that now. So usually we plot for two variables when there are two like that, but when you have more, you can check how each one varies with the dependent variable. So for instance, in this case, we have the data and we have G3. So don't forget it's an XY thing. X will come first. G3 is Y, so we can put it first. And we have age. For instance, you can just put this. And now you get a plot of what it looks like. I don't know if you can see that in your own view there. Let me see if I can share what I have. Okay. All right. So this is the result I have. If you plot this, this is what you get. If you can see everything well. Okay. So you get this. And but you see that there is no relationship per se between the two, because you cannot see any positive relationship, neither can you see any negative relationship. What I mean is that it's not going straight like this, a straight line like this, or coming down like this. Okay, so that's that about that. Okay, so that's how you plot. So you can do that for all the other variables. But in order to put a function here like this, you need something called, I think, the line function. The line function, if you want to put something Hello, I don't know if you can't see. I think my share kind of paused. Hello.
Yeah, we're with you. Can hear you.
Okay. My screen kind of paused. That's why I'm trying to see if I can release it. I don't know what happened. All right. So you need something called a line function. And the line function, if you can, okay, let's see. Maybe I can go back. Okay, I'm back. The line function. So supposing we wrote whatever we wrote here the other time, we'll need to put something like, no, after plotting this, and it's out. So we plotted what we want to plot, but we still need to write plot, or rather line model. Okay, this is not working. Okay, for ease of we could put whatever that model is there. You could just pick it there. So for instance, you have 5, 7, 9. If you have x1, I think, and then you have x2 there, but should work. Is it lines model? But x is a list, but does not have components. Why? Okay, there's a way you put your line, even if I can't work on that now. I think basically you plot x and y. So we've done that for this. You need to do that for the other ones. Two x plus 5. Let's see. Not working as you should. All right, so there's a way anyway to plot this. I'm coming. Let's see if I can find help. But as regarding your second question, sir. Hello. Hello, can you get me, sir? All right. So I can't really, I couldn't really get your words.
Yes, I was actually referring to some, do I call it types of ANOVA now? Okay, so we have different types that can actually show significance, difference in significance. There's one that actually categorized them to A, B, and C. So I don't know if you can replicate that here. Can we?
Like I should talk about like the ANOVAs that you can have, analysis of variance.
Yes.
Okay.
I know there's one that categorizes them, it groups those that are significant into the same subset. So it subset them to A, B, C, D, E, F, depending on the data. So I want to know, is it possible with her?
Yes, and like as you just said now, it is possible to do many of these things, but there's an issue. The issue is very simple. Analysis of variance is a topic on its own. You can do all of that with R, but it's not something you can cover now, because it has to be, you need to explain, okay, this is how you do what we call RCBD. That's one of it, randomized complete block design. It's a design anyway, but the way you analyze zone variance is different. There's another design called the Latin square design. And then there's a basic one, which is the beginning, called the completely randomized design. So you do analysis of variance for all of these. Actually, there's a relationship between all of these designs I just mentioned now and the regression analysis. So that's why I use ANOVA in all of them. But
so we can also do DOCAN with her, right?
Yes, you can. You said? I didn't get you very well.
DOCAN, you can run DOCAN.
Yes, it's possible. So all of those analysis of variance, you can do them with R. Most of them, okay, and the ones that are common among them, their functions are already written in R. They are ready-made, like they are available in as a package that comes with R, like the default. But some of them, especially the ones that are not common, you need to go and download. You just get a package, a library, and then when you open it, you can get something that will help you on that. So that's a different topic on its own. You have to start learning how to use something called AOV. So, but we cannot cover that currently. Okay, I think
thank you very much.
Your third question, sir. You asked the third question.
Okay, yeah. Because of our time, I would just like us to first. I would like to first appreciate the facilitator again for this detailed explanation. So this is a move again, and then all of us who are moving, who will be following this move, should join our community, because we are going to continue this series. And then I would like you to see, we have dropped a link that if you are not a member of the community, to join the community, so that you can get updates on events like this, especially on R. So thank you very much. Thank you everyone for staying to the end. And thanks to our facilitator once again. And we hope to having you another time for AI every day and even subsequent trainings at DSN. Okay, so in the absence of question, I would like us to call it a day, and the resources will be shared with everyone that joined. The recordings to this class is on our YouTube channel, so you can always check our YouTube channel for the recordings of this class. So thank you everyone, and do enjoy the rest of your day. So thank you, facilitator. Okay, bye.
All right, bye. Thank you. Thank you, everyone.